in this video, I shall demonstrate the DC test of a 3-phase induction motor using wet lamp signaling. This test is designed to measure the stator resistance of the induction motor, a key parameter for its equivalent circuit model. So this is the simulating model. The DC test involves applying a DC voltage to the stator windings of the motor with no induced voltage in the rotor and reactance being zero. The only limiting factor for current flow is the stator resistance. So let's look at the simulation setup. So this is the simulation setup. Okay, this for simulating model that I developed. The key component include DC power, the DC power source connected to terminal of the Y connected stator windings, and a synchronized machine block configured as a squirrel cage induction motor. And we have display block to monitor the applied DC voltage, VDC, and current IDC. So now let's run the simulation for 10 seconds. As you can see, the results are displayed here. A DC voltage of 8.065 and a DC current of approximately DC current. So from the result, we get from the simulation, we can calculate the stator resistance using Ohm's law. R equal to V over I. So just substituting the values from the simulation give us the value of R, which will be used in subsequent tests. And that concludes our demonstration of the DC test for a 3-phase induction motor. So this test provides essential data for analyzing and modeling the motor's performance. And for the block parameter, the configuration, we use the rotor type squirrel cage because squirrel cage rotor is the most common type of induction motor rotor, especially in industrial application. And mechanical input, we use torque TM. Sebabnya the motor's mechanical input is configured as torque because this test does not involve rotation motion. So tak ada motion, rotational motion tak ada, sebab the rotor is stationary. Dalam kata lain, no mechanical speed is involved, so the torque input is used to define external condition, always acting on the motor. And the reference frame, we use rotor sebab since there is no induced voltage in the rotor during a DC test, due to the absence of alternating flux, using the rotor reference frame reduce complexity without impacting the accuracy of this particular test. So the summary is this configuration is chosen because it aligns with the simplified condition of the DC test. So this is for test 2. also demonstrate the block rotor test of a 3-phase induction motor using MATLAB Simulink. This test is essential for determining the total dependence, lock rotor resistance, and lock rotor reactance of the motor, crucial parameters for its equivalent circuit. So, this simulation model, the block rotor test is performed by clamping the motor shaft to prevent rotation and applying a reduced 3-phase voltage to the stator. This setup mimics a short circuit condition in a transformer, allowing us to measure the series impedance components of the motor. So for the block rotor test, the key component include 3-phase voltage source, VAA, VBB, and VCC, supplying balanced voltage to the stator terminal. Second, a synchronous machine block configured as a squirrel cage induction motor. We have RMS blocks to measure the phase voltage, phase current, and the short circuit power, PSC. And outputs for electromagnetic torque and rotor speed, which confirm the motor is stationary during the test. So we run the simulation. Run the simulation with a reduced voltage of 1 volt. As you can see, the result for phase voltage, phase current, and short circuit power. We repeat the test for voltage of 2 volt, 3 volt, 4 volt, and 5 volt to observe the change in this value. Using the simulation results, we can calculate the motor's equivalent impedance, resistance, and reactance. So the manual calculation in the report, in the final report. So the conclusion is our demonstration of the block rotor test for 3-phase induction motor. This test help us understand the motor's impedance and resistance characteristics under loop conditions, vital for performance analysis. So that's it for test 2.
Okay, welcome to the part 3 of our project series. In this video, I will demonstrate the number light test of the 3-phase induction motor using MATLAB Simulink. The test instruction for determining the magnetism, reactance, stator, copper loss, and rotational loss of the motor. The number light test is similar to the open circuit test in transformer. In this test, the motor runs freely without any mechanical load, while the stator terminal are supplied with the rate, voltage, and frequency. The motor operates near synchronous speed where the slip is close to 0. Okay, I will run. Okay, for the yearly simulation model for the number load, voltage source, synchronous machine block, RMS block, speed and torque output, constant voltage, and frequency input. Okay, I will run the simulation. As you can see, the motor operates at nearly synchronous speed. The measured results are voltage is 21500, volt. Okay, for the current is 777Y 1 ampere. Okay, the power consumed is 75.5 watt. Okay. Okay, from this value we can calculate the magnetic reactance, stator copper loss, rotational loss. Okay, for the calculation, this conclude our demonstration of the number light test for the 3-phase induction motor. This test provide valuable insight into the motor, magnetic branch and loss component, which are essential for each performance analysis. For the final part of our project series, in this video, I will demonstrate the simulation of torque speed characteristic for a 3-phase induction motor using magnet simulating. This test is critical for understanding the performance of the motor under varying loads. The torque speed characteristic curve is an essential tool for analyzing an induction motor performance. It helps us understand how the torque varies with the speed under different conditions such as starting maximum torque and steady state operation. Okay, this is the simulating model for the torque speed characteristic simulation. Key components include voltage source, 3-phase sine generator, a synchronous ignition block, step input and sample and hold block, torque speed output RMS block. Okay, I will run the simulation. The step input apply a lot torque at a specific time and the motor responds acknowledging. You can see the rotor speed, the start at synchronous speed at decrease as lot torque is applied. Electromagnetic torque increase to balance the lot torque as shown in the torque speed curve on the XY graph. For the analysis, the torque speed curve reveals the key point in motor performance: static torque, pull out torque, steady state operation. For the conclusion, this includes our demonstration of the torque speed characteristic simulation for a 3-phase induction motor. This test provide valuable insight into motor performance, helping engineers design systems that maximize efficiency and reliability. Okay, that's all from us.